So I think many of you are familiar with the importance of nonlinear dendritic integration. Indeed, a few speakers have already highlighted their contribution to capturing realistic network dynamics, as well as improving artificial neural networks. I think a similar argument should be made for axons, a point Professor Graham alluded to on Thursday. Here you see on the left the voltage profile of a single backpropagating action potential over time and space along the apical trunk of a dendritic tree to a branch tip. On the right, you see the forward propagation of an action potential from the axon initial segment through a myelinated axon and its submyelin spaces. The principal axon exhibits even more nonlinear integration than dendrites on multiple levels across a comparable distance to that which you see on the left. So, essential features of neural membrane are the integration and propagation of voltage signals. Put simply, neural membrane computes voltage signals. Now, in addition to wiring the brain in a particular way, axons often form a major part of a neuron's computational surface or interface as they compose the majority of its membrane. For comparison, here are the much smaller dendritic trees of layer 5 pyramidal cells with respect to their axonal trees, which you see in the remainder of this image. Embarking on a grander project to solve axonal integration, we began with solving the passive or leak structure of myelinated axons. This was enabled by whole-cell recordings at the soma and axon end over hundreds of micrometers. With fully factorial Monte Carlo-based optimization, we numerically integrated voltage signals over the axon to infer its passive properties. Axial resistances along the axon core and the submyelin spaces, and transverse resistances and capacitances over the axon membrane and myelin sheath. Now, these passive parameters being solved, we could account for the experimentally measured voltage propagation over space and time. Here, in the axon core, across the myelin sheath, in the axon core, over space and over time. And these properties turn out to dominate signal integration in axons. So now a natural next step was to include the active properties or nonlinear ion channel kinetics in our models and begin reproducing the recorded action potentials propagating over the same axonal surfaces. We employed a similar optimization technique, although with many technical adjustments, to solve the active structure of myelinated axons. Here you see an example of the search space. So first, I'm going to obviously go into greater detail in my poster session, what you see here above, which is essentially the paradigm itself. And below, you have, again, an example of an axo-somatic recording generating axo-somatic voltage traces. And these are used to infer the active properties that we are solving for, right? So we're doing numerical integration of the voltage transients as well as other state parameters. And this is just to give you an idea of the search space that is traversed in that optimization process. So this is what voltage propagation looks like over the active axonal tree. And here we're not only dealing with the myelinated axon, which you see here, but also the entirety of the tree, the soma, as well as a number of dendritic processes here next to the soma. And just to be clear, this model also has dendritic integration, which could not be seen in the video as much, but we really do model all the way out to the farthest apical reaches of the tree. And of course, you can see that even for a single spike, these depolarizations in the dendrites sculpt the shape of the action potential. So with that, I would like to briefly acknowledge the many wonderful people who helped produce this work, and look forward to your joining me during the poster session.